relation just as I showed you yesterday. So today we will take it to a bigger mesh, right? Like we can think about a system and then we will derive a matrix, okay? And we will solve a problem today together, okay? So today you will learn it in depth and based on yesterday's knowledge. So let me just quickly go through the yesterday's knowledge that we learned yesterday. So I said that we will talk about the Galerkin finite element method, and then a special example, computational issues, element matrices, global assembly, MATLAB, and so on, right? So now we can see here that we have a differential equation. Now the point is that the difference between partial and ordinary differential equation is that the dependence on the variables, right? If it is depending on more than one variable, or we are in the 2D or in the 3D. So currently we are only in the 1D and the differentiation is only with respect to X. So we are talking about an ODE. We have two boundary condition, initial condition and the boundary condition at 0 and L, and we are using it in the least square sense, okay? And you can see that these are the 3 points along the x-axis, 3 points along the along the graph for the function. Now I will use during this lecture interchangeably u or y, so please do not be confused, okay? So yesterday we discussed about the Galerkin finite element method. Now students, what we do actually, the tilde means that this is an approximation, and we are saying that we can write the solution as the linear combination of the norm of the basis, okay? And the use values, the functional values or the values of y along the graph, okay, at different locations, at discretized places. And what we discussed yesterday was that if I divide my domain into small patches, what will happen? We can see here that actually I have a rectangle, but from this rectangle you can see that I have got the bases, that is n1 and n2. And another important thing is that in one rectangle there are only two lines, right? Two diagonals. And next, for example, this red line is shared in the other element, and then this green line is shared in the other element. So remember that we are now talking about elements, and these elements are connected with each other. You can even see that this is the connection point, this is the connection point, this is the connection point, and with respect to the, with the help of the basis as well, okay? And you will see the magic that we will obtain a matrix for one element. For the other element, we will combine these matrices and we will go to a bigger matrix. All right, so basically there are two matrices of interest: mass matrix and stiffness matrix. Okay, so how we define these matrices? We have this differential equation, these conditions, this is the approximate solution. Now the meaning of R is residual, okay? And I'm saying that if I am using this approximation, I will put a tilde here, and then I will substitute this u tilde into this equation, and I can further write it like this, okay, in the summation convention. Now I'm saying that my residual is orthogonal to the basis members, right? So therefore it's integral uh, with the phi I is equal to 0. Now with the help of this, we also call it weighted residual, and we will discuss it in detail today. So we can do some integration and integration by parts. We can reduce it and we can further simplify it. This part is called stiffness matrix, this part is called mass matrix, and this is the function vector. Remember that in today's example I will not consider this part because yesterday we have already discussed the mass matrix. So the first quick example, or the introductory demo, I will talk about the mass matrix, but in the detailed example we will not talk about mass matrix today, but tomorrow we will definitely talk about the mass matrix. Okay, so let's go to the next slide. Here I showed you how to derive the basis or the trial functions, and then remember that we can always transform these into xi or x as shown in the lecture notes that I have shared with you. Okay, so then I've showed you the formula for the components of the mass matrix M11, M12, M21, and M22, and then I asked you to provide me the answers. So I hope that you'll soon send me the answers. Now the next topic, which is the most important topic, and the previous one was only the basic introduction, quick introduction. Now let us go to the topic in more detail. So the basic concept is basis function and view versus element view. Now, how will these bases govern the elements, or how will these bases will help us to approximate the numerical solution? Okay, so now we talked about the mass matrix. So the correct answer for the other components of the mass matrix is given here. You can compare your assignment with this answer, and similarly you can obtain the stiffness matrix. Okay, now today's lecture is based on the examples, two examples taken from this book, Fundamentals of Finite Element Analysis by David Hutton. And the lecture notes provided in this book are very nice, very helpful, and very easy to understand. Okay, so let us go through it together. The method of weighted residuals is an approximation technique for solving boundary value problems that utilizes trial functions. Remember, the trial function is the basis that we derived, satisfying the prescribed boundary conditions, and an integral formulation to minimize error in an average sense over the problem domain. The general concept is described here in terms of one-dimensional case, but as is shown in later chapters, extension of 2 or 3 dimension is relatively straightforward given the differential equation of the general form. Now, I better mention here that it is not that straightforward, and it will take some time, and that is why we will depend on MATLAB or any other software to solve the partial differential equation in 2D or in 3D. But to do it manually, let us talk about a 1D case. Okay, this is the differential operator capital D, Y instead of U now I'm using. And these are the conditions at A and B. Now, Y static is actually Y tilde. Okay, so I can write it as a linear combination of the bases, and this ci is actually the y1, y2, and so on. Okay, so do not be confused. Now we have a task here. You can they have asked you to use the Galerkin method of weighted residuals. Weighted residuals, just as I have showed you in the trivial example in the beginning. So this is your homework for today. You will submit this homework by 15th of June, okay, in 5 days time. So and the hint is that page number 133, I will share the book with the CR, but I want this manually, like handwritten work, and you will show me your performance on a piece of paper. You can scan it using your mobile phone and you can upload it on CU Online. Okay, so the question is that you will write it in the weighted residual forms. Okay, this differential equation, and these are the boundary conditions, and solution is also given to you, but you will derive it by yourself and show me. Right, so now let us talk about the Galerkin finite element method. Now, what is the Galerkin finite element method? The classic method of weighted residuals described in the previous section utilizes trial functions that are global, that is, each trial function must apply over the entire domain of interest and identically satisfy the boundary conditions, particularly in the more practical cases of 2 or 3 dimensions. This is what we have already discussed. So now this is the differential equation, and these are the conditions. Now the most important thing is that, students, the problem domain is divided into m elements. Please make a note on your notebook. We are now going to divide it into m elements. Let's say m is equal to 10, and then of course how many edges are there? M plus 1. Okay, so values xi of the independent variables, so that x1 is equal to xa, xm plus 1 is equal to xb. Okay, so we will never miss the boundaries, the starting and the ending point. Okay, now this is another example of dividing the domain, and these are the examples of the trial functions. Okay, you can see that the sum of these two trial functions is equal to 1. Okay, and now if I am talking about the interpolation function for a subdomain, I'm saying that I've got the basis functions like this. And if I connect these two, 1 and 2, with each other, can you see that they are now sharing n1 and n2, sorry, n2, and then they are sharing it, and then you have n1 and n3 here, right? So next is, you can see here, this is another example. I have got here the generalized version, and here I have got, like, for example, this is n1 starting from the boundary. Then I can also make it like this is the shift function, then even from here, and then from x3 to x5. I will explain it in a minute. Okay, so an approximate solution is assumed to be in the form of y tilde y steric. I've written here tilde steric interchangeably. I will use this word. So I is equal to 1 to m plus 1 y I n I. Okay, ni are the basis functions. Yi is the value of y on the graph at that point. Okay, so where yi is the value of the solution function at x is equal to xi, and I is the corresponding trial function. Note that in this approach, the unknown constant parameters here of the method of weighted traces become unknown discrete values of the solution function evaluated at specific point. Now let us come to the point, students. Now can you read the definition of the trial functions here? Ni is x minus xi minus 1, xi minus xi minus 1, and now you are confident about this part because we have already discussed it with an example. So you are saying that Ni is defined in this way if x is from xi minus 1 to xi, and Ni is defined in another way if you are talking about the interval xi to xi plus 1. Remember that you have 3 points. Here you can see that, for example, here this is xi minus 1, xi, and xi plus 1. So for this part, the basis, even it is obvious from this graph, the line equation is different. The line equation is different. So this is how we have defined here Ni, and for xi minus 1 to xi and xi to xi plus 1. Okay, and it is 0 for x less than xi minus 1, of course, and for x greater than xi plus 1, because we are going to remember, students, that we are treating every element individually first, and then we will add it up. So that's why we are saying that before this or after this, we are considering it 0. Okay, this must be clear in your mind. So now clearly in this case, the trial function are simply linear interpolation functions such that the value of the solution in this interval is linear combination of adjacent nodal values, right? So we are saying that y static is actually the linear combination y2 and 2 plus y3 and 3, and we have already defined the n2 and n3, so we can substitute it here and simplify it further. So now when we talk about the residual, we are actually saying that it is actually the approximate